Hello. So this is my first class with you, the first semester students. What I will be teaching you is Unit 4 of the syllabus. Unit 4, if you look at the syllabus that we had provided in the group, it is about integration. So basically, what we will learn here in Unit 4 is about integration, but since you are in the first semester, we will not be doing the complicated things. It will just be some kind of a revision of the things that you had done earlier when you were in lower classes. But of course, there will also be some new things. In integration, over here in Unit 4, we will be learning about the techniques of integration. So when we are saying techniques of integration, it means how exactly do we integrate? And also we will be learning some applications of integration. And you will also first learn that integration are of two types, indefinite as well as definite. And after learning that these things, how to integrate them, then we will proceed to a few applications of integration. So most of the things over here you have learned, only some new things are there. Let us just go ahead. So what exactly do we mean by integration? Maybe you have learned in earlier classes, in your lower classes, that integration, the symbol for integration, it is this one you had learned. And you remember that there is that something which dx, and also you will be having a function here. Okay, so you will have this form fx dx. So whenever we are saying integration, we should first mention how many variables does the function that we have to integrate have. For example, over here we are having only one variable. So sometimes in your higher classes, you will be learning about some more complicated types of integration where we are having more than more than one variable. That is, we can have 2, 3, 4, or as many variables as you like. So over here, what we will be doing in the first semester, it will be an easier one, which is a single integral. That is, there is only one integral sign of a function with one variable, and we will be having dx. Again, I repeat, you may have learned in your earlier classes that this symbol, this integral symbol, it's just an extension of s. Okay, because s, okay, if you elongate it, okay, you pull one from this side and one from the other side, you will be getting this symbol. So just by pulling this s, you will be getting the integral symbol. You may have learned about that. Okay, so why exactly does it come from s? Okay, because integration is basically summation. Okay, that is, we had learned that for summation, it is this symbol. So what I'm saying over here is integration is nothing but summation. That is, okay, we are just summing up things. Okay, I will explain. Okay, so just imagine this situation. So in your earlier classes, you had also learned about this formula, that the work done is equal to force into distance or displacement, okay, depending. okay, displacement. Okay, or work done equal force into distance, that is when the direction is specified. Okay, we will be using distance. Okay, so you can imagine this. Okay, there is a block over here at point A, and you want to move this block to point B. So you will be applying a force in this direction. Okay, you want to move it in this way, and you are applying force directly in this way. So if the force, let us say it is 5 units or 5 newtons, and this distance, okay, maybe let us say it is 100, that is from A to B, it is 100, then the work done will easily, you can calculate it by using this formula, which is 5 into 100. 5 into 100 will give you 500. 500 units will be the work done. Okay, so this is when the force, it is constant. When the force is constant, that is everywhere you are only applying 5 units when moving this block from here to here. That is, even over here, you are applying the same force everywhere. That is when we can use this formula, force into displacement. But in reality, applying the same force, applying the constant force, it's almost impossible. Okay, for example, if I move this raster from this point A to point B, we cannot guarantee that I am applying the same force everywhere. Okay, that is, I may also do it in this way. Okay, apply a very high force, and then I can do it more slowly, and then again I can just push it with a very high force. So what I'm saying is, the force that you are applying may not be constant as in this case. So what do we do then? This formula over here, it works only when the force is constant. But as I had illustrated, when the force is not constant, we will have to do some modifications to this formula. Okay, but then let us first think about a simpler example. Okay, again we are having this point A, point B, the distance is still 100. Now what I am doing here is I am dividing this one into some more portions. Okay, maybe, okay, C and D. Okay, A, B, C and D are in the middle. Again, I am moving this block from here to point B. But what is happening in this case is, for A to C, I am applying a force 5. And from C to D, when moving this block, when the block is over here, I move it again. But now I am moving it, say, let us with a force of 3 units. And from D to B, when the block is here, I move it again until it reaches B. I apply a force of, let's say, 10 units. Okay, then the work done in this case will be how much? Okay, now it will be different, because now what you will do is you will have to sum the work done for this portion plus the work done in this portion plus the work done in this portion until it reaches the point B. So, but when we are calculating the work done, we need the displacement. Okay, so let us just say that this one, okay, 20, 40. Okay, maybe this one is also 40. Okay, just as an example. So over here what I can do is, the work done, it's 5 times 20 plus 3 times 40 plus 10 times 40. 100 plus 120 plus 400. Okay, you can add this one up to get the total work done from in moving the object from point A to point B. Okay, so coming back again to this, now you see that the work done, it's no longer just force times displacement, it's actually a sum Force times displacement plus force times displacement plus force times displacement. The force is no longer constant. It is changing from 5 to 3 to 10. But we are actually employing this formula here, 5 times 20, because the force from A to C, it is constant. It does not change from A to C. That is why we can use that formula. Similarly, from C to D, we can use this formula. From D to B, we can use the formula force displacement, because the force is 10. It remains the same from D to B. Okay. So what we had done, okay, we had divided this one into intervals, and we are calculating the work done as a summation. Okay, now we are summing 3 parts. Okay. But again, like I said, the force that we are applying may not be constant throughout. That is, it changes continuously. Okay. You were saying in that example that, okay, we are applying constant force from here to here, and then we are applying another constant force from here to here, and then we are applying another constant force from here to here. This one is different, but it remains constant. But it can also happen that at each and every point from A to B, the force changes. That is, even for from here to here, the force is different. From here to here, the force is different. Okay, what do we do in that case? Okay, what we will do is this. When the force changes continuously throughout from A to B, what we can do is this. We can take a very small portion. We can divide AB, okay, I'm saying it, okay, that we can divide this portion AB into very, very small portions. Okay, call those portions as dx. Okay, maybe a dx there, dx here. Okay, very, very small. So, and we can assume that for this small distance, the force does not change. Okay, that is the force here. In this very small portion, it does not change. Okay, so once we do that, again we can sum it up. Okay, but summing up will be a bit difficult here. It will be difficult because we don't know how many of these dx are there. Okay, in fact, infinitely many of them will be there if they are infinitely small. Okay, that is so many of them. Okay, for each and every of these portions, what we can do is we can write something like this, f dx. Okay, but you should be very careful. If I write it like this, it gives an idea that the force is constant, which is not true. It is only constant for a very small portion. Okay, for a very small portion. But what we can also see from our discussion is, I am saying that the force changes everywhere. That is, the force changes with x. Okay, if the object is over here, then the force is different. If the portion of the particle is here, then the force is also different. That is different from this point. Okay, it will of course be constant in a very small portion, but it will be different from another small portion. Okay, so what we are doing here is, okay, we are actually summing up. Okay, the force over here, f dx, plus another force over here, which is again constant, f dx. Okay, we can do it throughout. But again, these forces are no longer the same. Okay, maybe it will be f1 here, and for this point it may be f2, another force here, which may be f3. So many of these. Okay, we are adding them all up. Okay, but again, we cannot guarantee that there will be only a finite number of them. Okay, Maybe there can be 10, 100, thousands. Maybe we cannot even count such forces, okay, because we are dividing this portion into very fine intervals. So what do we do in that case? We are getting an infinite summation, infinite sums. Okay, so many sums are over here. Instead of writing it like this, okay, as infinite sums, we can easily write it like this: a to b f x dx. Okay, that is the work done. It is force times displacement, but the force depends on the position x, and the work done, it's calculated from a to b. Okay, so what I want to say is that when they were telling that the story about s being converted to this symbol, it is actually summation. Okay, because I want to interpret integrals as an infinite sum. Okay, so this very small demonstration will maybe it is making you clear about why we consider integration as an infinite sum. Okay, but that is exactly when we are having the limits, okay, from a to b. Okay, so we are considering it as an infinite sum, okay, when we are having the limits from a to b. Okay, but we can also interpret integration, indefinite integration, in another way. So what we had learned is, okay, there is an integration which looks like this, which we are calling it as a definite integration, definite integral. Okay, by definite integral, we mean that we are having the limits a and b. Okay, and over here, when we are having no limits, we are calling it as the indefinite integral. Okay, so we had interpreted integrals as infinite sum, but also we can call it as the antiderivative. Okay, the indefinite integral, we can also call it as the antiderivative. Okay, why exactly do we call it like that? Okay, I will give you an example to make it clear. Okay, let us see the first example. Okay, I will just give you an example. Okay, so if you differentiate x squared, okay, how much will you be getting? Okay, if you differentiate x squared, you will be getting 2x. Okay, but if you integrate 2x dx, you will be getting x squared. Of course, plus c. Okay, I will explain about this plus c in another after some time. But you are seeing over here that when differentiating this one, you are getting here, and when you are integrating 2x, you are getting x squared. Okay, so that is why we are calling the indefinite integral as the antiderivative. Okay, because it is a reverse process. Differentiation and integration, they are inverse processes of each other. Okay, but again, why plus c? Okay, why do we need this plus c? Because if you notice that if you differentiate x squared plus 1, okay, you will still be getting 2x. If you differentiate x squared plus 2, you will still be getting 2x. In other words, if you differentiate x squared plus c, you will still be getting 2x ddx x squared plus c, you will still be getting 2x. Okay, and because we remember that integration and differentiation, they are inverse processes, so that is why we can, whenever we integrate something like this, we will always have c. Okay, plus c. It is very important. Once you forget this plus c, everything is wrong. Okay, almost everything is wrong because we do require it. Okay, as you will see when we are actually studying differential equations. Okay, so remember that. Okay, when we are studying differential equations, this plus c will be very important. Okay, so with that being said, okay, we had learned that integral will be something like this, but in this semester sometimes, okay, they don't even denote as fx. Okay, simply, okay, they can even just write it as f dx. Okay, even if they write it in this way, just know that fx is there. Okay, so fx is a function and this one is the integral symbol. Okay, so keep that in mind. Sometimes instead of writing fx, they simply write it as f. Okay, with that being said, okay, we will see some very basic formula of integration. Okay, let's see this one. Okay, remember that indefinite integration, it's okay, indefinite integration, it is the reverse process of differentiation. Okay, these formulas you had actually learned when you were in your lower classes, but again, let us just go through them. So the first formula says that integration x n dx equal x n plus 1 divided by n plus 1. Integration sine x equal minus cos. And integration cos, it's equal to sine. Integration 1 by x equal ln x plus c or log x plus c. Okay, and integration e power x dx equal e power x plus c. These are the very basic formulas, okay, that you will be requiring. And also I should mention over here that in integration, particularly in these techniques of integration, you will be requiring a lot of formulae. So it is best if you write all the formulae in maybe in one piece of paper so that you can you can easily refer from that page. Of course, when doing exercises in the exams, it's a different thing. Okay, so I hope that is clear. But again, let us just take a look at this one. Okay, maybe if you're not clear, sine x dx equal minus cos x plus c. Okay, so you notice over here that okay, when you are differentiating sine, you are getting cos, but when integrating sine, you are getting minus cos. Why this minus? Because if you differentiate minus cos, if you differentiate what is on the right hand side, you will get what is on the left hand side. Dx minus cos x, okay, it will be minus, the minus you can take outside, dx cos x, and you had learned, okay, in your lower classes that dx cos x, it's minus sine x. So you will be getting sine x. Okay, so differentiation of what is on the right hand side should be the left hand side. Keep that in mind. Okay, so similarly for the rest of the formulas here, okay, you can easily do that. Okay, if you differentiate what is on the right hand side, you will be getting the left hand side. Okay, so now that we have learned about the techniques of the basic formulas, okay, let us learn what are the properties of integration. Okay, let's see. These are the three properties of indefinite integration. Okay, properties. Okay, so the three of indefinite integration. Okay, if you notice the first one, C, it is a constant. okay, you had learned that the constant can always be taken outside. So when you are having, okay, they did not even write dx, okay, but just know that it is there. C fx dx, the constant c can be taken outside of the integral symbol. C fx dx. Okay, so whenever you are having a constant that is alone, okay, you can always take it outside. The second one, let us see. Okay, integration fx plus gx dx. Okay, so over here you are having a sum of two functions. This one is a function of x. Okay, for example, x squared, it depends on x. Gx, okay, maybe x cubed or sine x. Okay, whenever we are saying a function of x, okay, for now let us take that it is an expression containing x. Okay, so we can actually split this one. Okay, integration fx dx plus integration gx dx. Okay, we can do this. Okay, so if fx is x squared, okay, we will be having x squared dx plus integration sine x dx. This one you had actually learned. Okay, so okay, similarly for number 3, instead of a plus we can have minus. Okay, for number 3, instead of plus we are having minus, the same thing. Okay, so these are the properties of indefinite integration that you must remember. Okay, you had done them in your lower classes, so that's why I'm just going through them very fast. Okay, so after learning the properties, what should you learn? Okay, of course, more formulas. Okay, it's not very clear. Okay, I will send this formula again in the group. Okay, but you must remember that, okay, we are having a lot of formulas in integration. Okay, so with that being said, let me just do an exercise which illustrate the properties. Okay, this is your first class, so it will be easier. Okay, let us just learn how to integrate, okay, maybe x squared plus sine x dx. Okay, so what should we do here? Okay, so if you are noticing over here, we are having fx and we are having gx. We can easily split them. X squared dx plus integration 3 sine x dx. So integration of x squared, which formula will you use? Okay, let me just see the formulas again. Okay, I know them, okay, but in case you had forgotten, okay, so that is it. Which formula will you be using for this one? The first, second, third, fourth, or fifth? Okay, if you notice that this one is actually formula number 1. Okay, instead of n, we are having 2. Okay, so you will be getting x power n plus 1, which is 2 plus 1 divided by 2 plus 1 plus, okay, constant, we can take it outside. Integration sine x dx. Okay, x power 3 divided by 3 plus 3 integration of sine x, which is, okay, it is formula number 2, which is minus cos x, okay, plus c. You must remember that in indefinite integration we will always be requiring that constant, and that constant you can only write it down, okay, you should write it down whenever there is no longer an integral sign. Okay, so over here I can easily write this one as plus c from this first integration, but I won't do that. What I will do, I will stick to that what I had just said, that is when there is no longer an integral sign, that is when I will write plus c. So over here I am still having an integral sign, that is why I'm not writing plus c, but afterwards, okay, over here I am no longer having an integral sign, that is when I write plus c. So you will be having this. Okay, so this is the first exercise, which is of course very easy. Okay, but what I will teach you now, okay, you must remember them. Okay, they will, the thing that I will teach you now will help you how to integrate faster. Okay, so what happens if we replace x by ax plus b in the basic formula? Okay, so instead of x, what if we have ax plus b? This one, okay, I am teaching you so that you will learn how to integrate faster. Okay, let's see. Okay, so we are having those formulas. Okay, number one, integration xn dx. Okay, so I'm just writing the formula again. Okay, let us see, x power n plus 1 divided by n plus 1 plus c. Okay, but what happens if we replace x by ax plus b? Of course, we will be getting a new formula. Okay, but you have to be very careful. Instead of x, I replace it by ax plus b power n dx. What will happen here is this. Instead of x, you can still replace it by ax plus b, so you'll be getting the same thing, n plus 1 divided by n plus 1, but you will also have to write in front of this one, you will have to write 1 by a. Okay, so you will be getting this. Alright, so this is what will happen. Okay, the formula takes the same shape, just replace it, but you will have to write 1 by a in front. Okay, divide the whole thing by a. Okay, you will see why, okay, in the next class. Okay, but I'm just teaching you right now. Similarly, we are having that sine x dx equal minus cos x plus c. So, if we are integrating sine, instead of x, we are writing ax plus b. dx, of course, over here we will still be getting minus cos ax plus b, but remember that we have to divide the whole thing by a. So divide the whole thing by a plus c. Okay, similarly, if you have 3x plus 1, okay, let me just do an exercise. Okay, exercise number 2. Okay, remember that this technique that I'm teaching you works for all the 5 formulas here. Okay, the basic formulas, it will always work with them. Okay, that technique. Okay, so let us just say exercise number 2. Okay, integrate e power 3x plus 1 dx. Okay, so this one, if you see, it will also take the shape of formula number 5. Okay, the fifth formula, if you see, this e power x plus c, it does not change. Okay, so e, but instead of x, I am having ax plus b. Okay, I'm having this one, where a is 3 and b is 1. So you will be having e power 3x plus 1 divided by 3. We have to divide the whole thing by a plus c. So we will be having this. So, okay, if you did not learn about this technique, okay, maybe you had learned some other techniques, but this one will actually give you a formula and just, I mean the answer in just one line. Okay, so with this, I end today's video.